Hey everybody, thank you very much for joining us. As always, please feel free to ask any questions along the way. And if you think you might like to come on the show yourself, please do get in contact. My details are on the channel's About page. Next week, we'll be talking with Scotty Allen from Strange Parts, but today's guest is Konrad Beckmann. Hello, Konrad.
Hi.
How are you doing?
Yeah, just fine.
Great. Would you like to introduce yourself? Give us a bit of a background on your life and who you are.
Sure. So I've been a software developer for a long time. I've been working in various software-related jobs and so on, and discovered embedded development and sort of dove into that. And basically learned by doing. So I've been doing like PCBs and FPGA projects and so on by my own. But yeah, mainly I'm a software developer.
Great. Okay. Cool. So I think if we start at childhood, your dad was quite a fountain of knowledge when it came to computers and technology. Can you fill us in a bit about that? What it was like growing up and
Yeah, sure. So during my childhood, my dad always had like computers opened up at home. We had motherboards and PCI cards and so on scattered. But that sort of woke some electronic interest in me, and
Okay.
I've always sort of been around electronics in some way. But I've never really like fully understood it and felt like that I understand it until much later. But
Okay.
yeah.
Great. So I think you mentioned as well that you etched your first circuit board maybe at sort of young age, 10, 13.
Yeah, that's
like
right.
that.
So I remember in the kitchen with the UV lamp, we did some etching back when I was like 10 or 13 or something like
Yeah.
that.
Was this kind of a kit that you guys did together, you and your dad, or how did that
It
come
was
about?
actually a tiny PIC programmer that you connected to the parallel port, if I remember correctly. So one of those really old school.
Yeah. Okay. And then presumably, as you were doing a PIC programmer, you did stuff with PICs as well at that time. So a little bit of software maybe, or
Yeah.
is it more for him that you got involved in, or?
Yeah, I was never good at PIC programming, and I gave it a lot of chances, but the whole bank switching and it's a bit of a pain. I just after I discovered STM32s, I just
Never
don't
look
want
back.
to go back.
Fair enough.
Yeah.
Fair enough. Cool. I think from then on, you sort of moved on to a bit of comp sci at uni, and you said earlier that it's a lot of maths heavy theory, that kind of thing. Can you talk a bit about your experience there?
Yeah. So when I joined the university, the computer science stuff, I like the programming things were super easy, but everything else was super hard.
Right.
So I kind of felt out of place, and it was very theoretical.
Okay.
But yeah, I stayed for 1 year, but after that, I went on with a job instead.
Okay.
So,
and that first job was?
So it's a company called The Astonishing Tribe.
Okay.
We did user interfaces for mobile phones.
Okay. Yeah.
And lots of interesting customers like Samsung, Motorola, and other big players.
Nice.
And
okay, was that kind of before Android, I imagine? And
yeah, it was just in the shift. So I started there 2008 and stayed for 5 years.
Is this what we call a feature phone? I can't quite remember what the definition of feature phone is, but like a color screen.
The clamshells and with the soft buttons and hard keys and all of that.
Okay.
But also some touch stuff, like just it was in the transition period. We were, it was a lot of fun because there was so much happening. Like every year was different. Every phone you
big
could
progress
see.
each time. Yeah.
Because nowadays it's all the black screen. It's just a brick.
Brick with a bit of shiny on the front. Yeah.
But there are these foldable screens these days, which are pretty cool. But
yeah.
Most of them look pretty much the same.
Okay. And so I think you focused then on the app side of the mobiles. Is that right?
So actually we
user
did
interface
so actually it was like a rendering engine, and I worked with the integration of that to customers. So I did like low-level debugging and high-level stuff as well. So it was kind of a mixed bag. But yeah, I remember debugging some issue where we had to go into the kernel and like really go to the low level touch input, get the latency down and stuff like that. It was a lot of fun.
Are we talking Linux kernel still, or are we talking something different?
No, that was
maybe
like
Palm OS,
proprietary.
That kind of
proprietary OS, like monolith OS.
Okay.
Yeah.
Very good. So since then, you've done quite a broad range of software. I think you mentioned Sony Mobile, Samsung, and things. How did you see that industry progress over time? You know, how did it come along? Now, obviously, we've got Android and security is massive and all this kind of thing. I presume back in the day it was a little bit more fend for yourself and fingers crossed everything works.
I'm not sure how much I should say, but like I don't know.
No.
It has become boring, to be honest.
Okay.
It was more crazy and exciting previously.
Yeah.
But anyway, it's been fun working in that industry. But,
Sure.
but personally, I felt like I'm pretty much done there in that space.
Yeah. So I think a little while ago you then made the shift slightly from sort of the high level software to more embedded stuff. Can you talk a little bit about that?
Yeah, so I got the opportunity to work at a company called Anima, which made a watch called Konrad, which is an analog watch with sort of a Bluetooth microcontroller. And I had the chance to start working there, and I took it. It was outside of my comfort zone because it was like really low level with FreeRTOS and a real embedded project, so to say.
Yeah, nice.
And I came from like Android and proprietary OS and stuff like that. So yeah, it was
all of a sudden you're squeezing onto a tiny micro and concerned about battery usage and that kind of thing.
Yeah, exactly.
Okay. So this watch, I think you have one. Are you willing to show it? Is that something you can put on
sure.
stream? Yeah.
So let's see how it's looks like
let
this.
me do that as well. I think there you go. Very nice. So this is analog. It's got hands and points at things, but it's a smartwatch, I think you said. Can you talk to us a bit more about sort of what's going on there and how it works, why it's smart, that kind of thing?
Yeah, so it has the nRF52 based microcontroller inside, and it connects to your phone, and the phone can push notifications to it, and the buttons you press can feedback, so you can like dismiss calls, and you can get different information.
Yeah, that's awesome. I love the old analog sort of mechanical side of things. So I like the idea of a smartwatch that's a little bit more mechanical. That's awesome. So since then you I'm not sure if you're still working with them or if you've moved on.
No, I moved on, but I stayed in the embedded industry, so to say.
Sure. And I think you said you're getting more and more involved in things like schematic review, bring up, more involved in the hardware side of things rather than just the software.
Yeah, that's right.
Like, how's that going?
I mean, it's going pretty well. It feels really nice to work close together with the hardware and be involved early on when we sort of, let's say, design a new product and do prototypes with, let's say we're investigating a new sensor. We might have to make like breakout boards or collect data and stuff like that. So I'm involved in designing, not actually doing the PCB work, but like being involved in like, we should have this pin and some, because sometimes you can get like presented with, here's the product, now write software, and that's kind of annoying.
I'm familiar with that one. Not an ideal place to be.
No.
Okay, so to extend that, then you're obviously from your sort of public online persona, you're doing a lot of hardware stuff, and that's presumably to sort of extend your skills out into that world. Is there anything in particular you want to start with in sort of your hardware experience?
Yeah. Where should we start?
Lots of things. Should we start with the Nintendo Game & Watch?
Yeah, let's do
a whole pile of reverse engineering.
Yeah, that's right.
Maybe a year or so ago with stack smashing.
Yeah. So it looks like this. So basically it contains a microcontroller and an external flash. And the sort of what we wanted to do was to dump the internal firmware, and in order to back up like a perfectly clean image of the microcontroller and the external flash as well, in order to be able to write software for it, but also be able to go back again.
Okay.
So in order to achieve that, we had to execute arbitrary code, essentially.
Yep.
And to achieve that, stack smashing, he found a way to alter bits on the external flash that became sort of the correct or the intended bits on the internal.
Okay.
When it was decrypted. So the reason why this was possible was they used STM32's AES encryption in counter mode, which essentially splits up your flash into, 16 or 32 byte chunks, but each chunk has its unique key and does XOR for each byte, which means that if you flip one bit will be, or 1 byte, and 1 byte will be flipped on the in the memory. So because of this, we could actually dump the internal RAM, or not because of that, but let's say they used RDP level 1, which is a lockdown mechanism in the STM32, which allows debuggers
That's
to be
the
attached.
readout protection, is that right?
That's correct. So the STM32, just to give an explanation, we have the 0, which is full access, 1, which is what they were using, and 2, which is fully closed down. Then you can't even connect to the JTAG.
Okay.
But you can get around that too.
So with level 1, you can't pull an image out until you full chip arrays, for example. Is that right?
That's correct.
But you can connect JTAG and get going.
Yeah, and you can dump the RAM. So instead of the RAM, there was content that was decrypted from the external flash. So because of that, if we flip 1 bit and we compare 2 RAM images and we see, oh, here's 1 bit or 1 byte that has been flipped, then we know sort of the relationship between that. And later on, Stack Smashing found where the Super Mario ROM was located. So that way he could flip bits and change, basically change the entire ROM. So with that knowledge, we collaborated and found a way to change code instead. So we wrote a really quick and simple payload that basically copied the internal flash memory to RAM, because RAM is a lot bigger than the flash on this one.
Right.
So we could copy the whole thing. And we could copy this because, when the STM32 is running code, it has full access to the flash. But once you attach the debugger, you get cut off.
Right.
But so the idea was that we write the payload to the external flash, and then that copies the contents to the RAM, and then you connect the debugger, because then in the RAM there will be a fully decrypted the full dump of the internal flash.
Yeah. Okay. So that was kind of a multi-phase, multi-step approach to getting into it. If I remember correctly, it was kind of poke at the external flash. So that means you took a full dump of that and you kept it safe, I presume.
Yeah. So we wrote a tool which has like 4 steps. The first one is we upload a program to RAM and execute that.
Right.
And that extracts the external flash, which is encrypted. But now we have it is like, instead of having to solder onto the flash and do like a flash dump, we can do that through the STM32, even if it's locked down. Even if it's locked down. And then the next step is to do the RAM dump, so that we know the decrypted stuff. And then we download that and do a patching of that. So using this and the flash, we can get the keys basically for these blocks. And then we do the patching with the payload, and then we upload that. So that is like the destructive part, where we actually change the external flash with our payload. And then eventually we restart the device and it executes our payload, and then we dump the internal flash from the RAM. And at that point, you have now a perfect replica of the internal and external flash.
Amazing.
So at that point, we do the unlocking, which is like really destructive. Then it gets wiped. And then we flash it back. So it's like the full circle, but now it's unlocked.
Yeah. So at this point, do you have a plain text image in the external flash, and you know what the internal flash contains, therefore you can sort of leave it in readout protection 0, is that right?
Almost. The external flash is still encrypted, but in the internal flash dump, there are keys so that we can decrypt it. So essentially, we can do anything.
Nice. Okay. Very good. And is that external flash then encrypted on a per device basis, or is it kind of the same across all of them?
It is the same. Yeah.
Okay, so distribution of these images is not it's not a matter of you can't because it doesn't work on others. It's just a matter of copyright and protecting yourself.
Yeah. So exactly. So there's no,
Okay.
there shouldn't be any legal issues with this. It's only code. Yeah.
Yeah. Brilliant. Okay. Very cool. So that was maybe a year and a bit ago, perhaps. It's crazy how time's been flying recently.
Yeah.
And since playing with the Game & Watch, I think you said that you just wanted to do more with consoles.
Yeah, that's right.
Yeah, talk to us a bit about how you sort of got to that mindset and where you went with it.
Yeah, so basically 1 year ago, last summer, I sort of needed a summer project, and I was kind of fed up with the Game & Watch because I had been spending a lot of time porting emulators, and I felt like I was done. Like the community is still alive, and there's still new emulators being ported as we speak, which is really cool.
Just to clarify, then the Game & Watch is running an emulator, is it, of the NES, or?
Yeah, so
I wasn't sure if they'd maybe re-implemented it to run on a small device or something.
Yeah, so the original device contains emulators for the on the Mario device. It's only an NES emulator and a Game & Watch emulator, but then in the Zelda one, there's a Game Boy emulator too.
Okay, I hadn't realized that.
So what we ended up doing was to port the RetroGo project as a starting point, and then we added a bunch of stuff to that. So
right.
Nice. With that we can emulate a lot of different systems. So for example, you can run Sonic on it if you want.
Oh, amazing. Very good. Okay, so sorry to bring you back on track then. We were talking about wanting to do more with consoles and
right, exactly. Yeah. So I felt like, okay, it's kind of fun with the games consoles and stuff. So I just had a look at what there is out there, and with the NES and SNES, they're kind of fully understood more or less. Like to me, it didn't feel like I could give much new to that whole scene. But the N64 was still kind of the odd one out. There seemed to be like a bunch of stuff that is still kind of unknown, and we can still discover things, and it's still kind of interesting. So what I did was I took one of my FPGA boards that I had designed previously. It's the Killsight board, which is a ECP5 based board. It looks like this.
Okay.
There we go.
Nice.
So
what are we looking at here?
So this is an ECP5 FPGA from Lattice, together with an FT600 USB 3.5.0.
Okay, and is that RAM on the right as well?
That's right. It's SD-RAM.
Nice.
Nothing fancy. Kind of slow, but good enough you can boot Linux on this thing.
Oh, brilliant.
So using that previous project, I was like, if I connect this together with a breakout board for the cartridge, I could make my own cart.
And so is that breakout board something the community have produced and you've just made use of, or is that something you've had to do a bit of reverse engineering?
But I based it on an open source cart. Okay. So I took an open source design and removed basically all the parts and cut it a little bit and just put a big fat connector on it, and
nice.
That was it.
Okay.
So I made that breakout board. I connected the wires and wrote some HDL. So I used Lytix in this project. Lytix is really awesome. I think you probably covered it in previous episodes, but essentially it allows you to pick a bunch of useful stuff for your FPGA projects, such as a SD-RAM controller, CPU, and just glue them together in one nice go.
It's kind of a design your own sock type thing, isn't it? It's
exactly.
Fantastic.
Yeah. So I took that and just implemented a N64 cartridge module, which has like direct access to the SD-RAM, because the thing with the N64 bus is that it's very timing critical.
Okay.
We're talking about like less than 300 nanoseconds for the response time, like from that you get the address until you have to have the data ready. It's
Sure.
it's really short. So if you have
Okay.
stuff like a DDR memory or I don't know some more fancy stuff, it's basically might
Impossible
not
to
be good.
service it. Yeah.
Yeah.
Okay. So, in terms of that, the bus again, I presume because you have this open source, people know how the carts work and everything. That's kind of well understood. So you could follow public information effectively to figure out how the console was driving the cartridge,
Exactly.
and then how to respond back. Yeah.
Yeah. So regarding the bus, there's a lot of good information on the internet about this publicly.
Mm-hmm.
So and there's a community, the N64 Brew. They have a Discord and a wiki, and there's a lot of really knowledgeable people there who helped me out when I was working with this as well. But
Okay.
all of the like raw information is out there,
Brilliant.
which is really cool.
Okay.
So doing that, I was able to basically boot Mario from my FPGA based cartridge.
Mm-hmm.
And I got into writing some homebrew and got comfortable with the whole software side as well.
Nice. So was this kind of your first big FPGA project then? Wow.
Sort of like this. Like I've been doing a bunch of FPGA things where I've never really had a use case, but here I had an actual practical use case.
Okay, nice.
So just to go back a little bit in time, I made this other board, the Pergola.
Oh yes,
it's also an ECP5 based. Come on, there we go. ECP5 based FPGA board, and with that, I designed a bunch of PMods like the HDMI PMod and a bunch of other stuff, where I was able to create DVI signals with high resolutions and stuff like that. It was really fun, and I learned a lot on that.
Brilliant. Okay, so how did you find implementing the cartridge interface from the FPGA side? Was that reasonably straightforward? You mentioned timing already as a pretty key constraint. Was that actually quite difficult to manage the timing? And
yes, I mean, I needed raw access to the SD memory, which is a little bit. I mean, it's a little bit finicky. So basically, I get a raw read port to the SD memory instead of going through the. So in Litex, you have this bus where different peripherals are connected, among them memory. So you can make a memory request on the bus where you like ask, hello, I want to read this address. Can you please give the data to me when you have time? And then sometime later, maybe you get a reply. But here we cannot do that. So I have like a dedicated read port where I directly say, I need this memory now.
Okay. So this is kind of dual port RAM type read port is what you're talking about. It's obviously, or perhaps not.
It's an arbitration thing. So basically, when I say I need memory, then I get memory.
You take control over everyone else on the bus.
Yeah, exactly.
You come
Which
first.
is it's sort of an acceptable compromise. Like if you do CPU stuff at the same time, you might have issues and so on. But it worked for me, and it's basically a proof of concept. And so implementing the N64 bus protocol was a lot of fun. Where I had to react on the signals and do the correct process and so on. And Litex helped me a lot because they also have this LightScope, which is a logic analyzer built in. So you can basically say...
I was wondering about that because it looks like quite a wide connector.
It is. And I did have my SLI logic connected on like as many pins as possible. But the built-in logic analyzer is really helpful.
Okay. Amazing. So talk to us about the sort of the flow, the use case, how it works. Do you start up a CPU, plug it in via USB or similar, and load a ROM onto the RAM, and then hand the RAM over to the N64 interface? How does it kind of work?
So in this one, sort of, yeah. So so when it, how should I explain this? The full boot flow is there is a CPU, a soft CPU, which runs firmware. And in that firmware, I have code that could potentially load a ROM from SD card and load that into SD-RAM.
Right.
And then at some point it will be done. And at that point, it will be safe to like turn on your N64. So it's kind of crude, but it works.
Okay. And then do you hold the CPU in reset or similar to stop it accessing the bus, or what happens there? Stop accessing the RAM, sorry.
Now that I think about it, I think I just make sure not to.
Make sure nothing happens. Okay, fair enough.
Yeah, it's kind of crude. Yeah.
Fair enough. Cloud Love has just asked, what's the FPGA board? What's the name? So I think you held up 2 boards so far.
That's right. It's called Killzip. I can send the GitHub address in the chat.
Sure. And the other one's the Pergola.
That's right.
Which I will find a link for as well. There you go. There you go.
Yeah, so I had these boards at hand. They were on my desk and just taking up space. So I thought, why not make something fun with it? So.
Fair enough. Very good. So that was the beginning of N64. You managed to boot Mario. Did you do anything else? Were there any other goals with this project?
So yeah, I just wanted to do as much as possible, to be honest.
Sure.
So I wanted to explore the video signals as well, and I wanted to grab raw video data and raw audio data, and I needed to stream this to a PC. So in order to do that, I used Glasgow. So
yeah,
I'll show you the board here. So this is the Glasgow Rev B, early one. And for those who don't know what the Glasgow is, it's an FPGA together with a microcontroller, which makes it nice and easy to do stuff like data acquisition and poke at various hardware in a very streamlined and nice flow, where basically you have one Python file that does everything. It does both the hardware description and the software on the computer side. So that made it super convenient to explore the protocols and iterate quickly.
So with the Glasgow, you were looking at capturing the audio and video, was it?
That's correct.
And I imagine that lots of consoles have got sort of capture cards and various other things going on to get access to this for whether it's just to record it or stream it or whatever. Was this kind of a new thing that's not really been done with N64, or is this just kind of a challenge to yourself? How did that go?
It was only a challenge to myself, but there are at least 2 commercial products out there today where you basically solder in a flex cable and have a quite big PCB, which does with an FPGA, which has it does the data acquisition and does the HDMI conversion. So you get like an HDMI port on your N64, and it does scaling and has a bunch of like fancy features. And I didn't really want to like compete or stuff like that. I just wanted to understand. So
sure, okay, no, that's fair enough. So you ended up with a solution that brought the video through Glasgow, through the FPGA onto the PC, and then was it playable? Could you stream it? How did that go together?
Yeah, exactly. So I wrote a program that took this data stream and turned that into a video for Linux device, like a virtual webcam.
Yeah.
So in OBS, I could use that, and the latency was actually pretty good. Like I could watch the OBS screen and play, and it didn't feel off.
Oh wow, that's amazing. I'm surprised, but well done. Okay, so at this point we've got a well understood cartridge interface. We've got the audio and video capture going. What was next in your N64 adventures?
Yeah, I don't really know. Maybe we do something proper.
Yeah.
So at this point, everything has been like throwaway projects. Not really a throwaway, but stepping stones.
Sure.
Just learning experiences. So basically, a few weeks or a month ago or something, I had a look at the project. So I wanted to make like a proper PCB with an FPGA for this cart. So I have like a 70% done PCB laying around where, basically an FPGA based cartridge. But I never finished it. But when I had a look at it like a month ago or so, and I thought, damn, FPGAs are really hard to buy. I'm never going to finish this project. It just feels pointless. So I remember I had explored the Raspberry Pi Pico a little bit, but I never really had a use case for it. Like it seemed really cool with the PIO, the programmable IO. but I didn't really know what to do with it. But I thought maybe I could interface with the bus. So just to give an explanation of what PIO is, it's essentially a small, like you have 32 instructions that run on the system clock speed, one instruction per clock. And you can do really cool stuff like reading all of the GPIOs in one go, like one clock cycle does that.
By all, you're referring to literally all, or all of a port?
Yeah. So there's only like one port.
Okay.
There are 30 GPIOs, and all of those are mapped into like a 32-bit word. Or not, that's not really true. But anyway, the point is that you can read multiple IOs and store them in a nice way, and then send them back to C code with a FIFO. And that way you can basically almost like you get almost FPGA performance for some use cases.
I've seen people doing some silly things with this. I think you may have been one of them crazy. As well. DVI from a PIO and things like that. It's
we can come back to that a little bit later.
Okay, sure, yeah.
But yeah, so essentially I took that Raspberry Pi Pico and thought, okay, let's see if we can do the N64 bus on this. So I don't remember exactly how it went, but I just set up like a basic project and did a stream and just went from a blank page. Like I didn't know anything about PIO. I know about the N64 bus, how that worked. But yeah, during that stream, we like set up the project and started with like very simple PIO stuff. And then I think Luke Wren joined from Raspberry Pi and helped out a lot with the PIO stuff. And we ended up almost getting it to work. Like we were so close. But
is this all in stream one?
Yeah.
Wow. Okay. Well done.
But it was like 7 hours or something. I don't know.
Oh wow! Goodness.
It was a tough one. But yeah, the day after, I like had a good night of sleep and went back to the drawing board a little bit, changed like I don't know 2 lines or something, and it worked.
Oh, that's frustrating, but well done.
Yeah.
Can you talk to us a bit about the N64 interface? What does it look like? Have you got address lines, data lines, like read write strobes? How does it go?
Yeah, exactly. So actually I can show you my screen.
Yeah, please do.
Where I have this all drawn out. So
cool, thank you.
All right. So what we're looking at here is this is the cartridge port, and it contains the AD means address and data. So it's a little bit annoying, or yeah, it's a little bit how it is. So you have shared data and address. So you have these signals, and then you have these ALE-L and ALE-H signals. So these signals, they determine when the high or low part of the 32-bit word is being sent.
Okay, so it's a 16-bit bus, but 32-bit wide, sort of the other side of the interface.
Exactly.
Yeah.
And then you have the read and write signals, which when they go low, you're expected to handle that. So when it's a write, then that means that the AD signals contain the data that is supposed to be written. And with the read, you should prepare the data that is supposed to be read. And when on the rising edge, it has to be stable.
Okay. Yeah. And so when these are both not asserted, do the pins then contain the address? Is that how it works?
Yeah. So there's a sequence of ALE-L and H, how they go up and down in a special sequence. But more or less, you can write a state machine looking at these.
Okay. I was kind of expecting it to be more of a dumb flash interface almost across the pins, but it seems like it's a little bit more special for them.
Yeah, I guess it's maybe like part of a copy protection scheme. I don't know, making it a little bit harder to clone.
Yeah.
I'm sure there were. I honestly don't know too much about the history. Like maybe there were like clone cards really early on. Who knows? But anyway, you can't just buy standard flash and connect it.
Sure.
You need to follow this address. Also for each read that is toggled, you increase the address.
Oh, that just happens behind the scenes. So you can just wiggle that on and on. Okay.
Exactly.
Very cool. You got cold reset there. Is that so that the cartridge can reset the console, or is it the other way around?
To be honest, I don't know if that is possible with this signal, but on the other side, it's like when you turn on the N64, this goes high.
Okay.
So I use it as like a start signal for that.
Yeah, sure.
There is the NMI, which is non-maskable interrupt, and that you can use to sort of interrupt the program and cause a reset.
Yeah, nice. Okay. And then last question on this, you've got SI clock and SI DAT.
That's right.
What's going on there? That's intriguing.
So this is the serial interface. This is mainly used for EEPROM saves. So I haven't implemented that yet.
Okay.
But so the save solutions for N64, it's a little bit convoluted. But you have SRAM, which is connected on the AD bus, like the normal.
Inside the cartridge, is that? Or is that on?
Yeah, exactly.
Okay.
And then you also have inside of the controller, you can connect a memory storage device to the controller. But then you also have the EEPROM in the cart.
Yep.
So this signal is used for that, but it's also used for an RTC clock for one game, I think.
Okay. It's kind of a peripheral thing that's interesting. There's a little bit. Yeah. Okay. Fair enough. Very good. Cool. So that's the N64 interface. How about the rest of the project? Can you show us a little bit about the Pi Picos that you're using and what's going on there?
Yeah, sure. So should I go back?
I don't know if you want to scroll around or.
Okay. So what we're looking at here is the future design of the Raspberry Pi or the PicoCart 64.
Okay.
So the current prototypes I have, they only use like either the Raspberry Pi Pico and basically nothing more, or a module, the RP2040 module from Solder Party, and some connectors. So there's like no more smartness than that.
So I think you had a couple of prototypes to show. Is that something you're willing to do?
Yeah, sure.
Yeah. So
I'll go back.
Yep. Yeah, go for it.
So let's see here. The first prototype is this one.
Okay.
And this one contains the RP2040 stamp from Solder Party.
And the flexi pins.
Yeah, exactly. So
fantastic. They're awesome.
And it basically enables me to use more GPIOs. So the Raspberry Pi Pico, which looks like this, it doesn't break out all of the GPIOs. So we are kind of GPIO starved. So we can't really interface with lots of peripherals with this.
So with the Pi Pico, as it's in that one you're holding up now, are you able to properly drive the N64 interface and it still works properly, but you can't do much else? Is that what you're saying?
Yeah. So I'm relying on the external flash that is on the Pico, which is only 2 megabytes.
Okay.
So it's a little bit limiting in that regard. You can buy AliExpress third-party pin-compatible-ish boards. They're slightly different, but yeah, with like one bunch you can use them. And they come in like 16 megabyte variants. But using that you can boot bigger ROMs.
Right. Yeah. So just out of interest, how big of a normal N64? How big would a ROM be?
So Super Mario is 8 megabyte, I think. Some games are 12, but some games are up to 64 megabytes.
Right. Okay.
So
that GoldenEye and things, perhaps.
It's actually only 12 megabytes, I think, or 16. 16. Yeah. So actually, that was kind of fun. So games that were 16 megabytes, they took up all of the flash, but I need firmware as well. Yes. So actually, I ended up implementing compression, very simple compression. So what I did was I split up the ROM into chunks, and I filter out so I only have the unique ones. So if there's a duplicate, I only store one.
Right.
And then I make a mapping using basically just I shift the address so that I know, like I have the chunk part and the offset part.
Okay.
So using the chunk part, I know which chunk to use.
So that's effectively the chunk part is the high address bits. And then the offset into the chunk, is that what you're saying, is the low address bits?
Exactly. Okay. And then I just have a very simple table that maps this. And it's very simple and stupid, but it works.
And so you're actually able to retrieve or recover enough space just by deduplicating blocks.
Yeah.
Wow, I had not
because
expected that.
there is some duplication. Mainly, there is some empty space in the end
Yep.
in most games, and that is enough for me to fit the firmware, because the firmware is really small, because I don't do much.
Okay.
So that was kind of fun. So
Awesome.
I was able to put 16 megabyte games on it. Of course, not guaranteed that every will work, but still kind of interesting.
So where was I going? Sorry, I've lost my train of thought. So with the Pi Pico in its stamp variant, there you've got all of the pins broken out. Is that right? And so you're able to do external memory access, that kind of thing.
Yeah. So the idea is to use this as sort of a development platform to test SD card access together with in the system and so on. To be honest, I haven't done much prototyping with it, but it allows me to do so. So I ended up thinking a lot and doing many iterations of a high-level design for how a proper card should look. And I ended up with a design where basically we have two RP2040s, and we have an array of 8 megabyte PS RAMs, so we get 64 megabytes. So we have 8 of those. And to address those, we have the chip select through a demux.
Okay.
So we have 3 bits of basically which address we want to use, which chip we want to use, and then also an output enable for that. And so it's all about pins with a RP2040, because it's so pin starved. I mean, it's you have 30 GPIOs, which is a lot, but the N64 bus takes up a lot of GPIOs.
Yeah, absolutely. So you've got potentially a 12 megabyte game ROM image, which you need to then present on these tight deadlines, 300 nanoseconds, I think it was, you said. Where's that coming from? Is that stored in Flash? Can you kind of preempt it and load a block into RAM? How are you dealing with that? Because I think you mentioned SD card just now as well, and that's feeling a little bit scary.
So for SD cards, we're gonna have to copy it somewhere. And that is where the PS RAM array comes from. So we sort of need some storage. We could also use like a big flash, like the NOR flash, 64 megabyte NOR flash, but then loading a game will take minutes because you need to erase all of that flash. It takes ages. So PS RAM is like the way to go. What was I gonna say? So all the accesses go to the external flash actually in real time. So it turns out that the access is fast enough. I think it's 160 nanoseconds from basically the request to the data. So what I do in code is that I prefetch, because when I get the address, I can sort of hint to the CPU that I want a certain data, and then that becomes a memory access, and it gets stored in cache. And then in the next cycle, the read signal goes low, and at that point, it will be in the cache, and I can just return this data very quickly from C code, and that takes like 160, 180 nanoseconds. But this is actually when we overclock. So it's possible. It's possible to run this without overclocking the Raspberry Pi Pico, but in order to meet the SRAM timings, which are even tighter, they are 200 nanoseconds. We basically need to overclock, otherwise it won't work with the commercial games. But for the normal ROM data, you can actually from the ROM configure the bus to run at a slower speed, so that you can you have time to present the data in time.
Interesting. Okay, neat. So I think one of your, I think it's work in progress still, maybe the schematic you just showed us actually makes use of 2 RP2040s. Is that right?
Yeah, that's right.
Can you talk to us a bit about what's going on there?
Yeah, right. So essentially, because we don't have a lot of free GPIOs, we need access to our SD card, and we need access to the Wi-Fi module, which we want to use. And everything should also be like firmware updateable in a nice way. So the idea is that we should have like a very simple bootloader on a shared flash between the RP2040s. And that bootloader contains firmware that lets the microcontroller know if it's 1 or 2. And based on that, we can also sequence the boot. So
sorry, just to clarify, you're talking about shared flash, as in these two RP2040s are connected to one flash which contains the bootloader.
Yeah, exactly.
Okay.
And the way, so this isn't tested yet, so who knows if it's gonna work. But the idea is that the flash is connected to all of the flash pins. So only one flash memory connected to both the chips.
Right.
And then we have this run pin, which if pulled low, prevents or resets the chip. Right. So we have like a pull down on one of them, and the other one boots first.
I see.
And then that run pin is then connected to a GPIO on the other one. Mm-hmm. That when it is ready, it can pull it high and then let the other one boot. So because of this, there shouldn't be a bus conflict with the chip select or clock or whatever. So once the first one is done, it copies the bootloader into RAM, and it's like done with the flash, and then it hands over to the other one.
Okay.
So it's still experimental. We don't know if it's gonna work. Who knows?
Yeah, that's very interesting, I have to admit. And then is there some GPIO pin which is strapped so that it knows if I'm number 1 or number 2?
Exactly. So I haven't figured out exactly which one I'm gonna use, but the idea is simple. We use the same GPIO number on both of them because it's in the bootloader. But in the first one, it will be high, and the other one, it will be low, or vice versa.
Okay. Amazing. That's quite cool. I like that.
Yeah, and the idea is that this bootloader will then load the application firmware from SD card, so that a user should only be able to like download a build from GitHub or the GitHub Actions, drag and drop it to their SD card, plug it in, and off you go. And in worst case, you need to update the flash. You can hold down the what's it called again? The ROM boot button. So basically, you hold down the chip select for the flash, which will let the ROM bootloader start. And that is super convenient in the Raspberry Pi Pico because that ROM bootloader contains a UF2 USB bootloader, which presents itself as a mass storage device. And if you're running Windows, for example, or Mac or whatever, you just drag and drop a file and you're done.
Off it goes.
So no magic software needed. It's perfect. So the idea is that this should be like unbreakable and simple to use.
Yeah. And then you've got the two processors. Obviously, they're a bit useless. There's no point having two if they can't talk to each other. So besides the boot sequencing and things, what's going on there? How do we sort of share knowledge or whatever it is they need to do?
Yeah, so this is also really experimental. So this would be like an experimental development platform.
Yeah, absolutely.
So because these are connected, if you see my screen, we could potentially maybe use this as a QSPI bus between the RP2040s.
Okay.
So I have a chip select, GPIO that connects them together so that we know if it's on or off. But the slave mode, I'm not really sure how that will work. That might not be possible. So either we should prototype this more, or I just do the hardware and see what happens. So as a backup solution, I have these two pins connected, which either work as a UART, which is UART. It should work, but it's really slow and kind of meh. So I also want to do SPI. As like a backup solution. And here I'm using like a IO pin instead of Musumisu. So the idea is that based on the commands, we know when to drive and be input. And this way we only use 3 pins like IO, chip select, and clock. But then on the other side, we need to implement a slave interface for this, which either I'm using like the hard SPI block, or we're doing this with PIO. And if we go for a PIO solution, we could do DDR, like we are toggling the clock and latch data on both edges. I don't know if this is feasible, or but I have a platform. I connect the wires so that I could do that.
So what's the expected, what's going to go across this link? Is that going to be accessing the ROM image data, or is it going to be loading the right-hand RP2040 is going to load it from SD card, send it over the link to the other side, or what's going on there?
Not really. So I wanted this link to be access to like Wi-Fi or SD card access directly, because on this SSI bus, we also are connected to the PSRAM array. So the PSRAM array, which contains the memory, it can be read and written by both devices.
Interesting. Okay.
So by using some synchronization and that we make sure that there is no bus conflict, we could, for example, load a ROM directly from SD card, write it to the PSRAM, and keep the other one in reset, and then let it boot, for example. That's the simplest way. And then when it boots, the other one boots, it will like be allowed to read from the PSRAM. But there are use cases like where you want to do stuff in real time. Like the application could, for example, ask the pico card, hey, can you copy this file from SD card to this address in memory?
Right.
And do like an off-board DMA, so to say.
That's very interesting.
So like there's a lot of potentially really cool features we could do here, but and I don't want the hardware to be limiting. So I want to connect everything and be able to do stuff. But off the bat, the firmware will be very simple. Like all of these cool features, they're going to come like
potential later. For later. Yeah. Okay. Interesting. So at this point, did you ever feel that actually RP2040 is not the right choice for this project, or have you is it more of a play thing to sort of see how it goes and just get a bit of experience and stuff? What's going on?
Yeah. So like the whole project started because I wanted to see if the RP2040 worked for this use case, and yes, it does.
Okay.
But having dual RP2040s or having something else, yeah, sure, we could go for something else as well. But it was kind of fun to use the RP2040 because it's super available. There are like millions available. You can just buy them.
They've done so well on that front. Yeah,
and they're so cheap, and it's kind of fun. So I'm gonna stick with it.
But perfect.
But I do have an ESP32 Wi-Fi module as well, which in this design will be optional, so you don't have to have it connected. So
very cool, nice. So talking about PIO again, I think you mentioned that you implemented the N64's interface in PIO. Is that correct?
Yeah, that's correct.
So actually, that's all sort of state machine and very basic. Is there any interaction at all from the CPU, or is it able to do everything it needs to from the PIO logic?
So the way it works is that it. Wait a second. I can show the code if I'm just.
Yeah, sure. Yeah.
Okay, so let me just dig up the code. Let's see here.
Okay. Sorry to put you on the spot. I'm not sure if you can zoom in. Yeah, perfect. Cool.
So
this is the PIO code for the N64 interface. Is that right?
Yeah, that's right. So it all starts with setting up the pin directions. What that means is we want everything to be inputs.
Right.
So, and then we use this wait, which basically waits for a GPIO number 17 to become high.
Okay.
And then we wait for the second one, the ALE, to also go high. So at this point, we are fairly certain that both of them are high, but we are not 100% certain because PIO doesn't. Maybe there's a way to look at multiple bits, but this is one way to do it. So at this point, both of them should be high, more or less. Then we wait for this one to go low, and when that happens, we get the low or high bits of the address.
Okay.
So we sample them into this called ISR, the input shift register. So in pins means that sample pins and consume 16 bits and push them into the shift register.
Okay, interesting.
So you can look at other things, and you can push other number of bits and so on. It's quite flexible.
Mm-hmm.
So then we wait for the other signal to go low, and when that happens, we have the low bits, and we do the same thing. So at this point, we have 32 bits in the ISR. So there is something called auto push, which basically, when you have filled up to a certain amount of bits, it will push automatically. But I opted for not doing that for simplicity.
Sure.
So what this means is that it will consume the input shift register, put that on the FIFO. So there's a FIFO memory between the PIO and the CPU.
Okay.
And if I'm not mistaken, it's like 4 entries or something.
Mm-hmm.
But for our use case, it's okay to just use one at a time.
Okay.
So at this point, it just pushes and it continues. It's not blocking, I think.
Yeah. Okay. So on the application side, on the CPU side, does that then get an interrupt, or does it unblock somehow? Sorry, this isn't supposed to be a code review.
I can show.
Just intrigued, yeah.
Yeah. So, we do this.
Okay.
PI get value. Right. This is my code. So does the state machine get blocking? So this one will block until push happens.
Nice.
So when this has executed, this gets executed, and we have a value. So at this point, I could print it, I could log it, and so on. And then, we continue. So going back to the PIO. So now we have to write some more code. So this is the pseudocode. So we're waiting for this signal to either go high, and if not, the state machine.
Mm-hmm.
But if this one goes low, we should go to the handle right. And if this one goes high, we should loop.
Okay.
So turning this simple code into PIO is not so simple. One way to
don't worry too much about step by step, but
sure.
The overview of the pseudocode you highlighted is very interesting to hear about. So
right, So the idea is that we have a tight loop here where we are. So in an FPGA, this all of this would be like one statement, and we're just waiting.
Yeah.
But because it is not an FPGA, it's actually sort of a CPU. We have to execute code. So here is like potential to miss stuff and so on. But it is good enough. So but essentially, this is what discovers if there is a write request or read request, or if the bus is restarting.
Yeah. Very cool. Okay.
And then eventually, we do this sort of push-pull thing where the state machine has reached a point where it knows I need bits from the C code. Okay. So I push an empty message, 0. And then in the code, I can look for this. So maybe I'll go...
That's just a synchronization point to that, I guess.
Yeah, exactly. Yeah. So I see this as like a command or address. So because the addresses are aligned to 16 bits on the N64, a 1 can never, the LSB can never be set.
Right.
So I use this as a write request. And if the whole address is 0, I interpret that as a read request.
Okay.
But otherwise, it's a valid address. So this is like the IPC, so to say, between the PIO and the C code.
Okay. Yeah. Cool. Thank you for showing us that. That's very interesting. I'm taking your screen off again, so you're welcome to come back.
Right.
So we just had a question again from Cloud Love. I love the Pico, but besides the Pico, is there any SBC that interests you? So
single board computer?
Yes. Yeah.
So I don't really know much about single board computers, and the Raspberry Pi Pico is more like a microcontroller.
Yes, yeah.
But regarding single board computers like the Raspberry Pi 0,
I think based on the way the question's written, I think we can include micros and stuff as well.
Right. Okay. Yeah. Right. So to be honest, I don't really have a favorite. I'm very used to using the STM32 for private projects because they are it's quite convenient.
Were ubiquitous.
Yeah, exactly. They used to be really easy to buy, but yeah, the software side is also kind of neat. Like it's easy to create a project and just get going.
Yeah, sure. Okay.
But yeah, I don't really have a favorite one. No.
No, fair enough. We touched briefly on the PIO DVI implementation a while ago, and you said we could potentially come back to that.
Yeah.
Is that something you'd like to talk about?
Yeah. So just going back a little bit with the Glasgow project.
Yeah.
So I did this video capture and audio capture using the Glasgow and doing an FPGA solution. So I thought, maybe we could do something with the Pico here as well. But video data is really high bandwidth, and we only have the USB doing what's it called again? The slow USB full speed.
Yeah.
So that is like not going to be enough. We need something more high speed. Then it turns out that Lugren implemented this DVI output where the Raspberry Pi Pico outputs an actual DVI-D signal like HDMI that you can connect to a monitor and get, I think, I don't know exactly which resolutions are supported, but yeah.
I have a feeling it was as much as 1080, 30 hertz or something ridiculous, but I may be completely wrong on that.
No, I think you might be right, yeah. But for our use case, we kind of need a frame buffer. And frame buffer is limited by memory size, and we only have 256 plus a few kilobytes. So we opted for a 644 by 480 frame buffer in 16-bit mode. So I thought, what if we combine this? What if we take the DVI and capture video signals and like stream it? And it turns out it almost works. We got really close, really close. And I think
now to clarify, sorry, you're looking at capturing data from the N64 into the PIO, twizzling it around, and then outputting as DVI.
Correct.
Right? Okay. Yeah. Very cool.
We cannot jump over a few steps there, but yeah. So essentially,
of course, I simplify, of course.
Yeah. No, but yeah. So I usually, when I do like interesting things, I want to stream those. So I did a stream where I took a look at this, and during that stream, we kind of went from a blank slate and had a look at the signals, capturing those, and outputting them into the frame buffer, and then streaming that frame buffer to using DVI. Yeah, and the annoying thing is that we got to the point where we could see Mario's face, but it was really garbled up. And we couldn't figure out what was wrong. Like the timings didn't make sense. Like the number of pixels per row didn't really match what it should be. They were like wobbling around a little bit. We got a little bit plus, a little bit minus. And going back to it and thinking about it, it's because we should use inline resistors to sort of match the impedance or reduce the rise time and ringing and stuff like that.
Right.
So I want to go back to this and give it a go again. It would be really fun.
That could be very cool, yeah.
Yeah, because then you could actually, I mean, you can't do stuff like scaling, and you might get some annoying borders and stuff, but essentially you get like an HDMI enabled N64 for $4, which is kind of neat.
Yeah, fantastic. Very cool. Okay. I think we're just about at time. Is there anything else you'd like to talk about or shout out about or anything like that?
Not really. I have a bunch of projects, but I almost never finish my projects except for the last one here, the Pico card. That's something I really want to finish. So
sure.
Yeah.
I'll put the link to your GitHub for that in the chat as well, just so everyone can see, and I'll try and include it on the description as well.
All right.
Because that's really exciting. I'd love to see where that goes. You've got some very interesting approaches with the two RP2040s.
Yeah, we'll see how that turns out. I mean, it might be that nothing works and we're gonna use UART.
No, fingers crossed for you though. Anyway, yeah, brilliant. Well, thank you very much for coming on today.
Thanks for having me.
Much appreciated, and fantastic projects. Good luck with the Pico card.
Thank you.
Next week, we'll be talking with Scotty Allen about his concussion new workshop and a couple of other things. But for now, it's goodbye from us.